Well, continuing our discussion about what makes redox reactions so much more violent, potentially, than acid-base or metathesis. In double replacement, what types of things did you look for in double replacement reactions? This is why, since this is a chemical reaction, a chemical reaction starts in chapter 4 and continues in chapter 5. And so what I'm doing is I'm kind of dipping into chapter 5. I've been dipping into chapter 5 because to give you extra time to absorb it rather than hit you with a test right away on that. You look for precipitate, For example, we talked about double replacement reactions like barium chloride plus sulfate, or barium ions and sulfate ions. Look for precipitate. We also talked about double replacement reactions leading to weaker acids, like going from hydrochloric acid to phosphoric acid. Or do you guys remember that? And so, precipitates. Well, what's special about precipitates? Stronger bonds, right? What's special about weaker acids? Stronger bonds. And so, in other words, we're just forming a little stronger bonds from weaker bonds. This leads to more stability. That's called a driving force. In nature, things try to go from high energy to lower energy. And so, what we're dealing with is we have the same charge on the atoms. We're just looking at, are we forming a better bond? Whereas in redox, we're totally changing the charge. There's actual, and looking at that sodium, that should give you an idea. The differences in stability, between a sodium with a 0 charge and a sodium with a +1 charge. It's just going, +1 in oxidation state. Other things aren't going to be nearly as violent as that, but sodium is. And so an important aspect of chemistry is to actually understand a little chemistry. And to understand a little chemistry, you have to do some memorization. You can't get around it. Okay. All right. Let's take a look at some others. If we continue on here, if we look at 4, actually, here, 3C, do you recognize that type of reaction right away? 3C. Disulfur dichloride plus ammonia yields tetranitrogen tetrasulfide plus, what's NH4Cl? Ammonium chloride plus, what's S8? S8 is called yellow sulfur. It forms rings of 8 sulfur atoms. What kind of reaction is that? Can you tell right away? A lot of people just look at that and in 1 second they know it's a redox. How did you know? So quick, because of sulfur, right? No. Sulfur was contained in compounds over here. Here it's positive, here it's negative, here it's 0. This is kind of weird because sulfur does 2 things here. Sulfur starts out at +2 and then ends up at what would you say here? Well, this is kind of an unusual compound. Well, maybe sulfur is a little trickier. Here, nitrogen is what here? Not +3. -3. Over here, it's so nitrogen goes from -3 to -3. Hydrogen goes from plus 1 to plus 1. And so maybe this compound is the electron-rich species or electron-poor species? You know, in other words, electron-rich species is called the reducer. The electron-poor species is called the oxidizer. Which one is the reducer? Which one's the oxidizer in this combination? Sulfur is the oxidizer, and nitrogen and ammonia is the reducer. Maybe. What happened? Well, it depends on this nitrogen over here. Now, what is this? And so it looks like some of the nitrogens nothing happened to. And so we look. Well, sulfur went from, well, this is minus 2, from minus 1 times 2 is minus 2. This has got to be plus 1. And sulfur went from plus 1 to 0. If it goes from plus 1 to 0, it must have gained electrons. And so over here, what is sulfur here, though? Normally when we do this, you know, we write the positive and then comes the negative. And so normally the negative part would get its normal charge. What's the normal charge on sulfur? Minus 2, which would be nitrogen would be plus 2. And so here, nitrogen's going from minus 3 to plus 2. So nitrogen is, some of the nitrogens are losing electrons. And the sulfur over here is gaining electrons because it's going from plus 1 to 0 and also plus 1 to minus 2. You see? And so this is kind of a complicated redox reaction because you know, the sulfur doesn't form the same product. Chlorine, nothing happens to. It just stays minus 1 and hydrogen stays the same. So this is a more complex redox reaction here. All right, going on to this one, what does this look like to you? What functional group? Can you tell? 3D. What kind of organic? Well, one, it's organic, right? What kind of organic? It's an alcohol, right? It's good. And so alcohols combust, form CO2 and water. What kind of reaction is combustion? Is that an acid base, redox, or metathesis? It's a redox, right? The oxidizer is O2, the reducer is the alcohol. Alcohols are pretty good reducers. And then we can continue on with some other reactions here. This particular one, 4C, I want you to name this one for me, Fe3O4. What is Fe3O4? You know what geologists would call Fe3O4? Geologists call Fe3O4 magnetite. It's a mineral, black mineral. Magnetite. But I don't want to use magnetite, which is a common name. I'd rather call it its normal chemical name, which is actually, this was going to be my quiz question today, but I decided I'm not going to do it. I'm going to do a different quiz question today. iron 4 peroxide. Iron 4 peroxide. Well, you know, the peroxide ion is O2, 2 minus. And so you're saying we have 2 peroxide ions, and we have how many irons? 3 irons, is that right? And so each of these irons is 4 plus. And that's going to give me a total positive charge of plus 12, balanced out with a total negative charge of minus 4. It doesn't work. Iron 4 peroxide does not work. We'll try again. I've given this on the exam before, just to let you know. Probably not last year's test. A lot of people got it. We talked about it. A lot of people didn't get it, even though I named it in class. I just couldn't remember. Maybe about, actually, thinking about it, I think I gave it 2 or 3 years ago on the test. And I think a lot, meaning like 20 or 30% of the class got it. 70 to 80% of the class didn't get it. And, you know, I wrote the name on the board. Well, think about this. We'll continue on. A lot of these stoichiometry problems are review. They aren't any harder than the Chem 4 ones. And so what I want to do is I just want to do a couple that are different than the Chem 4 ones that you probably dealt with. Some of these we have are going to be consecutive and simultaneous reactions. Two different categories. Consecutive reactions will just happen one after the other. And so in the synthesis of nitric acid here, you know, the first step in this particular synthesis, this is a 4-step synthesis. The first step of the synthesis is nitrogen with hydrogen. You know, this reaction isn't so easy to do because nitrogen is extremely, what? Nitrogen is extremely reactive, or nitrogen is extremely unreactive? Nitrogen is extremely reactive because, why would you say it's extremely reactive? Takes a lot of power to lose electrons. Power meaning easy to lose electrons or hard to lose electrons? Hard. And so I think you would, if it's hard to lose electrons, then you'd say it's unreactive. You know, and so hard to lose electrons. It's very hard to lose electrons. In fact, it's so unreactive because primarily it's a reason. We don't really say because it's hard to lose. It is hard to lose electrons because it's the third most electronegative element on the periodic table. You know, all those elements don't want to lose electrons. But, you know, unlike chlorine, you know, chlorine's hard to lose electrons, but chlorine's extremely reactive. Nitrogen's hard to lose electrons, but it's extremely unreactive. but this is just getting a feel, because you might think like oxygen, nitrogen being the third most electronegative should be as powerful or nearly as powerful as oxygen as an oxidizer, but it isn't. It's nowhere near as powerful as, in fact, chlorine's even less electronegative, and chlorine beats nitrogen by a significant margin as being a much more powerful oxidizer. Why is that? That just doesn't seem to make sense, right? I mean, here, or does it make sense? I don't know. Does somebody have the answer? Maybe, is the answer in your notes? Did anybody write it down? Check back in your notes earlier today. It totally makes sense that nitrogen should be a reactive compound because of its high electronegativity. Fluorine's the most electronegative, and I showed you the fluorine chemist handshake, did I? And then followed by oxygen, and then nitrogen. And so fluorine, powerful oxidizer. It's powerful enough to catch stainless steel on fire. Stainless steel, if you know stainless steel, it's hard. The stainless steel is really hard to oxidize. That's why it's so expensive. That's why a lot of people like it, because it won't rust like plain old steel. It depends on what grade stainless. They have different grades of stainless steel. You get like surgical grade stainless steel. That stuff doesn't corrode. It's going to cost you. Then 304. 304 or 430 will corrode. 430 is what they make a lot of kitchen appliances out of. That will eventually corrode. Fluorine will catch that stuff on fire. I used to work with fluorine, and we had a little safety device. This is a small cylinder of fluorine. One, you don't want to use big cylinders of fluorine. Too much fluorine gas. Two, you encase it in a steel box. Not stainless steel box, this is a regular steel box. I think it was 1/4-inch thick walls. That way, if there's a leak in there, it'll eat through the steel box. It'll take time to eat through the steel box before getting out into the lab. And then you just run away as far as you can. When I was working with fluorine, I heard lots of horror stories. I was working with seasoned fluorine chemists. The fluorine chemist handshake was one of the first things I learned about working with fluorine. Apparently, the fluorine chemist handshake came from this guy at Berkeley who worked a lot with fluorine. And then then I started researching it, and then I saw maybe it isn't as dangerous as I once thought it was. This is just trying to gather just plain, factual data. Because factual data, it's hard to, you want factual data to put things in perspective. And so there was a study in the 1950s, fluorine gas as a chemical warfare agent. And so they got a group of Army volunteers to walk into a fluorine cloud with a jar and a lid and go as deep into the fluorine cloud as they could stand, and then seal the jar. And then they, detect how many ppm or how much fluorine that a human could withstand, basically. And so after I read that, then I thought, okay, good, I'm not going to die if the fluorine escapes. You know, one time when I was working with the fluorine, I wore three pairs of gloves, the outermost being heavy gloves, and fluorine eats up everything. So I replaced all my valves and other stuff frequently. You know, but one time I waited too long to replace a valve, and the valve started leaking fluorine gas. And I noticed when I went to shut off the valve, my gloves caught on fire, and then I quickly shut off the fluorine because I had a leak. You know. But I wouldn't have noticed it unless I had the gloves were good reducers. I wouldn't have noticed it earlier. But anyway, getting back to nitrogen, nitrogen isn't a powerful oxidizer like you might expect. Why? Someone find it? No. Someone remember? Huh? Triple bond, right? The nitrogen triple bond's extremely strong. And so it's not very reactive. This first reaction is very difficult to do. Nitrogen with hydrogen. Lots of people have tried it to make ammonia because nitrogen is plentiful. This is called the Born-Haber reaction because they're trying to make ammonia fertilizer from nitrogen. It turns out some legumes can fix nitrogen. This is called fixing nitrogen into a compound. Beans, but to do this industrially is very difficult. Anyway, that's the first, and then the second reaction is easy. You can burn ammonia. You burn ammonia, you form toxic gas, of course, NO gas and water. You got to watch out too, because if you burn a mixture of ammonia, if you burn ammonia with methane, and there's some methane in there, you could form hydrogen cyanide, which is extremely toxic. So you got to watch out when you burn these things, forming toxic gases. Whenever we form toxic gases, we always make sure to do those reactions inside the hood. There are some people who Okay, that's the second. The next step is the NO that's formed is converted to NO2. This is a very easy reaction that happens. NO being converted to NO2. NO is colorless. NO2 is this orange, brown gas. That was coming off the ship in Texas City. So this was the beautiful orange smoke, and that beautiful orange smoke will react with water here. The beautiful orange smoke will react with water to form nitric acid and NO. And so this is a four-step reaction, so we've got to figure out how much nitric acid we're going to form. So they're asking how much nitrogen, hydrogen, and how much nitrogen and hydrogen and oxygen and water we need, I think. No, actually, nitrogen, hydrogen, and oxygen. And so what we have to do in a particular stoichiometry problem like this is, here in the first reaction we form 2 moles of ammonia. In the second reaction we consume 4 moles of ammonia. And so all we have to do is we have to balance the equations, not just within themselves, but we have to balance the equations between each other as well. And so what we do in this particular instance is perhaps we would double this one. So we go 2 nitrogens, 6 hydrogens, and 4 ammonias. So that we get 4 ammonias going to here, reacting with the 5 O2s. Now everything's stoichiometrically balanced between the first 2 reactions. In the second reaction, we form 4 moles of NO. And so we go down here, and we start off with 2 moles of NO in the third. So we should double this so that the 4 moles of NO are transferred here. And so double this one, which will give us 4 moles of NO2, but over here we consume 3 moles of NO2. And so we're going from 4 moles to 3 moles. That's not balanced, so we need to balance that. And so how would we balance that? Well, the easy way to balance it is well, if we need 4 here and we got 3, the easy way to do that is to multiply it by 4/3. Use fractions. That way the 3's cancel, right? And we end up with 4. But do we want a fraction there? That means we have to multiply 4/3 all the way through. It's okay, we can have fractions and we can deal with fractions and coefficients. But since we're left with 4/3 here, probably the easiest thing to do is to triple everything after that. Once we triple everything, then we balance everything between the reactions, and now we can just approach it as a regular stoichiometry problem, just doing mole ratios. Does that make sense? So it's not much more complicated than a standard stoichiometry problem. The other type of thing that we're going to encounter are questions like number 91. When you look at number 91, what is this? It's a solid mixture of magnesium carbonate and calcium carbonate. Magnesium carbonate and calcium carbonate is often found in rocks as a mixture. You know, like I think dolomite is a mix of magnesium carbonate and calcium carbonate. It's been a while. Is heated, and so we got a mixture of magnesium and calcium carbonate. It's heated strongly. When it's heated strongly, it decomposes. In other words, it undergoes a reaction in which carbon dioxide is given off, and a solid mixture of magnesium oxide and calcium oxide is obtained. You know, if you look at number 90, we call that a consecutive set of reactions. Number 91, when a solid mixture of magnesium carbonate and calcium carbonate is heated strongly, is this a consecutive reaction? First the magnesium carbonate reacts and then the calcium carbonate? Or is this what we call a simultaneous reaction? Well, this is what we call a simultaneous reaction versus a consecutive reaction. Now, the biggest error people make with simultaneous reactions is this. So this is number 91. So we got magnesium carbonate plus calcium carbonate, solid. This goes to magnesium oxide and calcium oxide and CO2. So we got magnesium oxide and calcium oxide plus CO2 gas. The biggest mistake is that people balance this. Just work at balancing. And so if we balance this, well, we got one magnesium, one calcium, two carbons. So we'll need 2 CO2s. This gives us 6 oxygens over here. 1, 2, 2 plus 4. That's balance. This is balance. This is a big mistake. Somebody tell me if they see why this is a big mistake. Here. Can somebody see why this is a big mistake? I'll tell you why this is a big mistake, because I don't want to spend too much time. This is a big mistake because do mixtures have fixed composition or variable composition? Is the ratio between magnesium carbonate and calcium carbonate fixed or variable? It's variable. If you get a bag of magnesium carbonate and a bag of calcium carbonate, can you mix those in any proportion you want? You sure can. You can mix them in whatever proportion you want. But the problem with this equation is what then? People, I don't know why, but on the exam about, you know, let's see, last time I gave this problem, the exam maybe about 20% of the students did this. 20% is too much, so that's why I'm talking about it now. Well, I talked about it then too, but people forgot about it at that time. And so no matter what I say, it's always the truth that Um, I think, you know, if I gave this problem this semester, I would suspect 20% of the people would do this. Just judging by how every semester has gone. But I'm hoping that this semester will prove me wrong, and I won't see this. Because this person did what to the mixture? By balancing the equation like this person did what to the mixture? They fixed the composition of the mixture, and they fixed the composition of the mixture to what? Actually, I'm done. I don't have to do any calculations, because if this were true, then this is a 50-50 mix of magnesium carbonate and calcium carbonate. And so what is the percentage? Oh, this is percentage by mass. That's a little bit more tricky because they don't weigh the same. This is a 50-50 mole percent, right? And since calcium carbonate is a little bit heavier, then that's going to have a little higher mass percentage, right? Because it's just a little bit heavier. So this is a percentage by mass. So I know it's a 50-50. I just got to figure out 50-50. How many grams does 50 grams of magnesium carbonate weigh? How many actually not 50 grams. If this is a 50-50 by mole, then the way I'd probably do it is I'd just do half a mole of magnesium carbonate. How much does that weigh? Half a mole of calcium carbonate. How much does that weigh? Total those up, and then grams of magnesium carbonate over the total, grams of calcium carbonate over the total, and I'm done. Right? Do you think that's right? No, that's not right, because how do I know it's, did they tell me it's a 50-50 mix of magnesium carbonate and calcium carbonate? No, I could have any amount, right? Magnesium carbonate, any amount of calcium carbonate. And so when I have simultaneous reactions like this, I always split them into two independent reactions. And so this is a big mistake. What we got to do is this. We have to treat those separately. The magnesium carbonate doesn't care if the does it care if the calcium carbonate's there? Oh, magnesium carbonate looks at calcium carbonate and says, okay, I got to react differently because there's calcium carbonate here. No, because the magnesium carbonate just reacts independently, because when you heat this stuff up, this is a redox reaction. Is this a redox reaction, by the way? Let's look at this carefully. It kind of looks like a redox reaction, doesn't it? But is it a redox reaction? Did the oxidation, why is the heater on? That I don't know. But have you guys been playing with the thermostat back there? No? You should give it a good whack or something. Well, anyway, getting back to this. What kind of reaction is this? Redox, acid-base, or redox, acid-base, or metathesis? Okay, first let's check redox. Magnesium is 2+, oxygen is 2-, which means carbon is +4. Carbon is +4. Oxygen, nothing changed. This is not redox. Is this a double replacement reaction? Metathesis? No. It's certain. Does this look like an acid-base reaction to you? Where's the acid? Where's the base? It doesn't look like, no. It doesn't look like an acid-base reaction at all. But this turns out to be an acid-base reaction. It's an acid-base reaction because this is not a Bronsted acid-base. You're very familiar with Bronsted acids and bases. Bronsted acids and bases are proton donors, proton acceptors. This is called a Lewis acid-base reaction. Lewis acid bases are different. They're electron pair donors, electron pair acceptors. And so, you know, it's there This is an acid base. And so this one doesn't care about the calcium carbonate. The calcium carbonate can react independently of the magnesium carbonate, and the calcium carbonate itself will decompose into calcium oxide and CO2 gas. Now, the question is based on the amount of I wonder why each time I wake this from sleep. Screw this up. Change this setting. All right, so what happens is 12.00 grams of CO2 are produced from this mixture. How much mixture do we have? 24.00 grams of mixture. And so based on knowing how much mixture, how many grams of mixture, and how much CO2 is produced, can we figure out what the percent composition of this mixture is? Yes. The reason we can figure out the percent composition is because per gram of magnesium carbonate is going to produce a different amount of CO2 than a gram of calcium carbonate. That's because they weigh different amounts. And so they'll end up with different numbers of moles. Different numbers of moles will lead to different numbers of moles of CO2, which leads to different grams. And so based on how much CO2 is produced, we should be able to determine what the percent composition of this mixture is. And which one produces more CO2 per gram? Magnesium carbonate or calcium carbonate? Which one do you expect to produce more CO2 per gram? This is a typical standardized test problem. They always ask, which one produces more hydrogen per gram? Which one produces more CO2 per gram? I'll give you a list of compounds. And so which one of those two will produce more CO2 per gram? The magnesium carbonate or the calcium carbonate? The calcium is wrong. It would be the magnesium carbonate. Why? The reason why is because magnesium carbonate weighs less per mole. And so 1 gram of this equals more moles of magnesium carbonate. 1 gram of this is less moles because it's heavier. Does that make sense? And so the more moles of either of these, the more CO2 you're going to produce. The magnesium carbonate will produce more CO2 per gram. It's lighter, so its molar mass is smaller. And so that means 1 gram is more moles of magnesium carbonate than 1 gram is of calcium carbonate. Okay. Actually, those types of questions you'll find somewhere in this book, in this chapter. So this is what we call simultaneous. You know, these reactions are happening simultaneously. And then you treat this. You know, there are different ways. You know, this is one of those what do we call them? Two equation, two unknown type problems. We got 2 equations. The unknown is how much magnesium carbonate. What's the ratio of magnesium carbonate to calcium carbonate? We don't know that ratio. And so we got 2 unknowns. We've got to come up with 2 equations, or we use the alternate method. What was the alternate method? Alternate to the 2 equation, 2 unknown method. The graph, right? I prefer graph. Well, the same thing with 92. 92 is going to be a 2 equation, 2 unknown. We got a mixture of iron 3 oxide and iron 2 oxide. Oh, actually, and found to be 72% iron by mass. All right, this is another redox reaction. It could be, or it could just be, you know, just looking at the differences. Which one has more iron per gram? Iron 3 oxide or iron 2 oxide? Which one has more iron per gram of substance? Iron 2 or iron 3? Which one has more iron? Well, I heard iron 3, but unfortunately iron 3 is wrong. Why is iron... this one you should be able to do in your head. Because if we divide this is why we like fractions sometimes. This would be Fe1O 1.5. We divide both of these by 2, right? And so for every iron, we have 1.5 oxygens. Over here, for every iron, we have 1 oxygen. And so we normalize it. That's called, normalizing. So Fe 1.5, FeO 1.5 versus FeO. Well, this is going to have more iron because this has more oxygen. And so per gram, FeO should have more iron. These are little tricks that you learn for answering multiple choice questions on standardized exams, but for standardized exams, speed is important. Otherwise, you could just sit there and calculate it. You don't have to know these little tricks if you got time. If you got time, it's no reason to do that. All right, let's take a look at another one problem, and you tell me. A 2.05 gram sample of an iron aluminum alloy, ferroaluminum, is dissolved in excess HCl to produce 0.105 grams of hydrogen. That's a combined hydrogen from both metals. What is the percent composition by mass of the ferroaluminum? And so, looking at this, is this consecutive reactions or simultaneous reactions? Okay. Well, consecutive reactions, the product of one feeds into the other. This is not consecutive. This is simultaneous. Now, when we deal with simultaneous in Chem 1A, do we combine the two reactions together, or do we leave them separate and let them happen at the same time? We do not combine. For example, you know how many people, if I gave this problem on a test, you know how many people will tell me they have 1 to 2 mole ratio of iron to aluminum? And they're going to tell me that, for every iron, there's 2 aluminums. Is that right? Are these reactions tied together consecutively like that? No, that's not right. In fact, this is a mixture. In a mixture, we can have any amount of iron and any amount of aluminum that we want. Okay, and so I wanted to emphasize that, because people, when they get multiple reactions like this, they get mixed up as to how to treat it. But this is one. Not all the problems are this complicated. Some of these consecutive ones are quite easy. Like, for example, if you burn methane and ethane, if you burn 10 grams of methane and 10 grams of ethane, how much CO2 are you going to produce? Well, that's simultaneous. We treat those as 2 separate stoichiometry problems. First, take 10 grams of methane and figure out how many grams of CO2. Then take 10 grams of ethane and figure out how many grams of CO2, and then combine it to get the total mass of CO2. That would be it. All right, and so that's this is pretty much chapter 4. I'll let you go through, and if you have questions on some of the problems, be sure to ask, and we can go through homework problems if you get stuck. Okay. What we're going to do right now is we're going to finish up the lab, and then I'm going to talk a little bit about, let's see, how much time we have? Another hour, right? Okay, we're going to finish up the lab, and then I'm going to give you another quiz. Get hopefully some easy points. We'll see.